Welcome back to Applied Physics. In this video, we'll talk about fluid dynamics. As an instructor, one of my challenges in teaching an introductory physics course is balancing between going into enough depth about every topic that it is interesting and informative, while at the same time spending little enough time on every topic that I can talk about everything that there is for me to talk about to give you a well-rounded sense of how things fit together in the larger picture of the study of physics. Nowhere is that more apparent than in fluid dynamics. I've been known to joke that for any video in this course, I could spend an entire unit, if not an entire semester, just talking about the concepts in that lesson. For fluid dynamics, it's a little bit more extreme than that. Probably for each sentence in this video, I could spend an entire unit of a course. This could be an entire graduate program just on the study of fluid dynamics. So we are really getting an overview of some of the basic concepts. I'm going to try to get into enough detail that it is interesting, but again, try not to get too hung up on the details because we could literally be here for years if we don't kind of gloss over a couple of things. And I'm going to start that right at the beginning. I've been using this term fluids to collectively refer to all liquids and gases. A fluid is any substance that is able to take the shape of its container. If you pour a glass of water into a shallow trough, it will spread out and fill the trough. In the discussion of fluid dynamics, we're going to talk specifically about incompressible fluids. And to within an approximation, we can call that a liquid. Again, there's a lot of stuff going on there. There are situations where liquids can be compressed. There are situations where gases can become incompressible. But as a kind of basic understanding, if you think about incompressible fluid as liquid, that's probably going to serve you well enough. So consider here the difference between that glass of water that will fill out the bottom of the container and a glass of air. All right, well, you try to pour the air out and you can't really see what happens. So instead, maybe think about a pressure vessel. If you have a large volume of air and you collapse it under pressure, you can use that air and squeeze all of it into a smaller container, such as a bicycle tire. That is definitely not something you can do with water. So that's what we're looking at here. We want something that you can't really squeeze down or you can't practically squeeze down. One of the amazing things about fluid dynamics is that there's not really that much of a difference that you have to take into consideration whether something is incompressible or not, but it is something to talk about and it's some vocabulary that you should be familiar with, so that's where I wanted to start. All right, so let's consider that we have some sort of incompressible fluid, some liquid, maybe water, flowing down a pipe. And now let's consider just a little bit of this water. And once again, I'm going to make a very bad approximating assumption that I can take this entire disk of water and it's all going to be moving at the same speed. In reality, there's friction involved, there's viscosity involved, the capillary action is going to cause the water to cling to the walls, all this stuff that I don't really care about right now. But we can think about this water that is flowing down this pipe. And after some amount of time, it will have gone from its starting point to some new point. And we can talk about the change in position here as the speed of the fluid multiplied by the change in time. Okay, that's the definition of velocity. But if we change perspective, instead of thinking about the movement of individual particles in this fluid, what if we think about ourselves as a stationary observer? Helps if my pen is calibrated. Right, let's say that I am sitting right here, and I'm just looking at how much of this fluid goes past me. Well, in the amount of time that I'm looking at, this delta t, the first bit of the fluid will have gotten all the way there, and then when that goes past, a little bit more will come in and continue on, but not quite get so far. A little bit more will come in and continue on, but not quite so far. And all told, all of the fluid that is in this space will be fluid that has gone past my observation point. We can calculate the volume of that by taking the cross-sectional area of the pipe and multiplying by the distance along the pipe, this delta S that I just came out with. And of course, just a quick substitution, that means that we've got the volume of fluid that has passed me by is the area of the pipe times the speed at which the fluid is going times the amount of time that has elapsed. Another interesting question, instead of how much volume goes by in a given amount of time, whenever we're talking about a given amount of time, it's often interesting to talk about a rate instead. We're going to call the flow rate capital Q. I have no idea why we call it capital Q. I think at one point in the past, capital Q was the default letter of, I don't know, let's just call it Q to be done with it. And now, like, everything in physics is called Q. All right, but let's go ahead and call this Q. And it's going to be the rate at which volume passes by. So it'll be the volume divided by the change in time. And if we just take this, we can just move this delta t over to the other side of the equation. And we get that the flow rate is the area times the speed. Ignoring the equation for a little bit, this idea of flow rate should make some sense. If we're thinking about a closed container like this pipe, or to get a little bit more practical, let's assume that this pipe is a garden hose. Given the rate at which water is entering the hose from the spigot, the water is going to flow through. And because water is incompressible, the rate at which water comes in and the rate at which water goes out is going to be the same. And if you are very clever, you can take advantage of that fact. I feel very confident in saying that at some point in your life, you have probably taken a garden hose, plugged the end of the hose with your thumb, and caused the water to apparently start moving an awful lot faster. And that is entirely by the assumption that flow rate is constant. Let's look at that a little bit mathematically. Let's say that we have a garden hose, and those are usually circular openings with a diameter in the ballpark of 0.75 inches. From there, we can calculate that the area is pi times the radius, which is the diameter divided by 2 squared. My calculator is happy to tell me that the area in this case is on the ballpark of 0.44 square inches. And if I have a flow rate of, let's say, 20 cubic inches per second. That's about 5 or 6 gallons per minute, which is pretty typical of a garden hose. Well, since Q is equal to AV, that means equivalently that V is equal to Q over A. So we can take that 20 cubic inches per second and divide by 0.44. My calculator tells me that that is about 45 inches per second. Or perhaps a little bit more useful, if I divide that by 12, I can write that as 3.8 feet per second, which is a little bit more common as a measure of speed. But now let's say that we want to plug that hole up. We're going to stick our thumb in the hole so that the area has been reduced to 0.05 square inches, about 10% of the original opening, which is, well, for me at least, about what happens when I stick my thumb into the opening of a garden hose. 90% of it is blocked by my thumb, the other 10% allows water to flow through. Well, in that case, V is still equal to Q over A, but now we have that 20 cubic inches per second, and we'll divide it by 0.05 square inches, and we get 400 inches per second, which is about 33 feet per second. The rate at which water is leaving the hose is the same, but in order for the water to get through that much smaller space, it has to leave at a much faster speed. So we can change the speed without changing the flow rate. You may have heard this sort of thing referred to as a release of pressure, and the math behind that really does check out. Remember that pressure is force divided by area. And here we have flow rate divided by area. So not quite the same thing, but if we have a larger area, we have a smaller speed. If we have a smaller area, we have a larger speed, because there is more force trying to build up from the pressure that is building up in the hose. Somewhat counterintuitively, that gives us a result where if you have a hose that has a lot of space, that's going to be a high pressure area. And if your pipe or hose or whatever it is shrinks down and collapses into a small space, that smaller space is going to be your low pressure area. This is one where I think it makes a little bit more sense to think about the analogy of traffic. If you've ever been on a large highway, let's say a 4-lane highway, where there is construction up ahead and your 4-lane highway collapses down into a single lane. In the part where there are 4 lanes, traffic will back up. You can think of that traffic backup as pressure building. And then you have to squeeze through the places where the lanes have compressed, and that causes everything to slow down. But then all of a sudden you are through. And once you are through, you are able to move again. And you'll see the traffic is moving much faster after the merge point than it was at the merge point. Your high pressure squeezing all of the traffic down has let go into low pressure where everything is moving quickly instead of being squeezed. So there is one interesting result that we can take in our fluids. If we have a lot of space, the pressure will be higher. If we have less space, the pressure will be lower, because the change from the high pressure to the low pressure causes everything to move faster. That whole idea is summed up in Bernoulli's principle, which tells us that the sum of the pressure and kinetic energy per unit volume is constant for fluid flow in a closed channel. The first time I encountered this, the amazing thing to me was these two measures: pressure and kinetic energy per unit volume. Right? Well, pressure in SI units we measure in pascals, and then kinetic energy per unit volume. Well, kinetic energy is generally given in joules, and volume is generally given in something like cubic meters. Now, a joule is a Newton meter, and one of the meters on the bottom will cancel out that meter on top, so we have newtons per square meter. And yes, that is exactly the definition of a Pascal. So the unit of pressure and the unit of kinetic energy per unit volume are the same unit of measure, or within a conversion factor of each other, which means that we can add them together. We will be able to add these things. One last thing I want to talk about in this video. I've used this phrase closed container a little bit differently than you might try to use it if you stop and think about it. A garden hose is not really closed in. There's an opening at the beginning and the end of the hose. The water comes into the hose, travels through the hose, and goes out the other side. But if you think about a spot in the middle of the hose, well, the only way to go is along the hose. It's closed in on all sides. Compare that to a river or a drainage ditch where there is no top, so the volume is able to go up, and worst case scenario, right, if enough fluid is flowing into the drainage ditch, it might overflow the drainage ditch, but it can do that. But what if we really did have a closed container? What if we had a container that was sealed everywhere? Well, completely sealed, that's kind of boring, right? If you have a steel canister with some fluid in it, okay. You have basically a soda can, but maybe not carbonated. Maybe it is carbonated, maybe there's some pressure involved as well. But it's inert. It's not going to do much of anything unless you have some way of causing a reaction to change the pressure inside, like you would in a soda can. All right, so let's get something where everything is completely sealed. The fluid cannot escape the container, but maybe there is some way of interacting with the outside world. At first, this figure is going to seem very contrived. I hope to convince you that this is something that can actually happen and even be useful. All right, so let's consider this U-shaped container. And let's put a movable seal, a piston, over here, and another movable seal, another piston, over here. If I push down on this piston, it's going to cause, I have no idea what just happened there. Oh, I do know what happened there. I don't know why it happened. There we go. All right. I'm going to push this piston down. It's going to cause the water, the fluid, to ripple across. Remember, we're thinking about an incompressible fluid, so it has nowhere it can go except to push this piston upward. Likewise, if I try instead to draw this piston up, it's going to cause fluid to come in its wake and drag this piston down. So the motion of one piston is going to be directly tied to the motion of the other piston. This is codified in Pascal's principle, which tells us that any pressure applied to a confined liquid is transferred without measurable loss through the liquid to all interior surfaces of the container. So what that means is if I put some load, actually let's put the load on the larger piston. If I put some load on this piston, that load is going to cause an increase in pressure. That increase in pressure is going to try to push on the walls of the container everywhere, and it is also going to push on the other piston. And it is those two pistons that are the points that are going to be interesting. So we can say that the pressure on the left and the pressure on the right have to be equal to each other. And if we remember from previous study, pressure is force divided by area. So the force on the left divided by the area on the left has to be equal to the force on the right divided by the area on the right. Now here's where things get interesting. Let's say that the piston on the left is a cylinder whose cross-sectional area has a diameter of 0.1 meters. Actually, let's make this even easier on ourselves. Instead of thinking about diameters, let's think about radii. The piston on the right has a radius of 0.5 meters. Maybe we'll tack a 0 in at the end here so we have a couple of significant figures that we can work with. All right, that means that the area on the left, remember area of a circle is pi r squared. So the area on the left is 0.031 square meters. And then the area on the right, will that be 0.25, a quarter of pi, which I used to know offhand, but I do not remember now. .79. we've got very appreciable differences. Now let's say that we're trying to lift something very heavy. And we need the force helps if I write what I'm trying to say. We need the force on the right to be 200 newtons. Well, rearranging this formula, we get that the force on the right is equal to the force, I'm sorry, that's not what I'm trying to solve for. I'm really making a mess of things today. We can write that the force on the left is equal to the area on the left times the force on the right divided by the area on the right, just multiplying both sides of the equation by the area on the left. Plugging in all of our numbers. Area on the left is 0.031. Force on the right is 200. Area on the right is 0.79. And when I crunch all of that, in order to get that 200 Newton force on the right-hand side, the left-hand side only needs a force of 7.8 newtons. Casting this example in a different light, what we have just created is a very convoluted lever. We are pushing with a small amount of force on one side, and we are causing an outsized amount of force on the other. In order to make this work, that means that we're going to have to put our small amount of force over a very large distance, and our larger force is going to go on a smaller distance, but it is a machine. We can use it to do productive work. We can calculate the mechanical advantage. There's something that you hope that you wouldn't hear again. Remember that mechanical advantage is the resistive force divided by the effort force. The resistive force is the force that we need. In this case, that's the 200 newtons that we needed to apply to lift something up. And the effort force is the amount of force that we put in this case, 7.8 newtons. And our mechanical advantage is 25 times in this particular case. Of course, that mechanical advantage also tells us the difference in distance. So we have to push down 25 times as far as we get pushing up. But this is the basic principle of a hydraulic lift. We can use a small amount of force to lift a very large thing by pushing the force on a much larger distance than the distance we're trying to lift something. With that, I think I have gone on long enough. I'll wrap this video up here. Thank you as always for joining me. I'll see you next time.